Let's talk about sign convention first. The figure that we see here defines the sign convention for beam bending problems. First, we have a coordinate system where the x-axis is pointing to the right and z-axis is pointing downwards. So using the right-hand rule, that would mean that the y-axis is pointing out of the paper. This cutting face here is called a positive cutting face. And the way we define the directions for the internal forces, including the axial force, the shear force, and the bending moment, is that if the face is a positive cutting face and the respective forces point in the positive coordinate directions, then it's considered positive. For example, NX here is pointing in the positive x direction, therefore NX is positive. QX is pointing in the positive z direction, so the shear force QX is positive. The moment MX, if you use your right hand thumb rule, the thumb is pointing in the positive y direction because y is out of the paper. So the moment is positive as well. Now, on the other hand, on the negative cutting face that you see here, the convention is such that if the internal forces point in the negative directions, then it is considered positive. For example, for the axial force here, NX points in the negative x direction, so it's positive. The shear force QX points in the negative z direction, so it is positive. The moment MX, using a right-hand rule, the thumb points into the paper in the negative y direction, so it's considered positive. For the distributed loading, downwards is considered positive. For the reaction forces, we typically assume them to be pointing in the positive coordinate directions. So all these reaction forces are positive. The applied force here is also positive, pointing in the positive z direction. What you see here on the left are the expressions for the internal forces and moments. For the internal axial force, Nx, is given by this expression, where Q here represents the distributed loading in the x direction, and the summation here represents all the applied loadings, including the reaction forces, also in the x direction. For Qx, Qzx here represents the applied loading in the z direction, and the summation here represents all the applied loadings in the z direction as well. And finally, for your moment, the big Qx here represents the expression for the shear force computed using this expression, and the summation here represents all the applied couples. Take note also that your shear force is related to the distributed loading by this expression here, which simply implies that the Qx over the x is equal to minus Qx, which means that the gradient of the shear force function is equal to the negative of the applied loading function. And the moment is given by this expression, the integral of the shear force, which means that the mx over dx is equal to qx, which means that the gradient of the bending moment function is equal to the shear force function. Now, these functions here are what we call discontinuity functions. You realize that they are all to the power of 0. So how do we define such discontinuity functions? Shown here on the left is the function x minus a power 0. The bracket here is a special bracket called Macaulay brackets. Now, for this special discontinuity function to the power of 0 is basically a jump function. So from 0 to a is basically 0, except that at point equal to a, it is equal to 1. Beyond a is also equal to 1. So it is a discontinuity function where the discontinuity happens at x equal to a. On the other hand, we have the power 1 function. In this case, the function is 0 from x equals 0 to a, and beyond a, it is equal to the function y equal to x minus a. This Discontinuity functions are used to represent the distributed loadings, which I will illustrate in a moment. The way to differentiate and integrate such functions is given by the two expressions below. The derivative of this x minus a power n is equal to, using the normal rules of differentiation, you bring down the n, and then the power, subtract 1, and that's the result. Now for the integration of such discontinuity functions, the normal rules of integration also apply. You increase the power by 1 and then you bring down the increased power and then add it to a constant. In this question, you have a beam supported on a pin at the end A on the left and supported on a roller at point B on the right. There is a distributed loading of 3 kN per meter from x equals to 0 to x equal to 2 meters. And then there is also a concentrated force applied downwards at x equal to 3 meters. The free body diagram of the beam is shown at the bottom. In addition to the distributed loading and the concentrated force, we also have the reaction forces at pin A, where Fax is the support reaction in the x direction, and Faz is the support reaction in the z direction at point A. Fbz is the roller reaction at point B in the z direction. Let us now write down the loading function in the z direction. The first term here represents the distributed loading starting from point x equal to 0, extending all the way to the end of the beam. But however, in reality, the distributed loading only is applied from x equal to 0 to x equal to 2. Therefore, we will have to subtract off the portion from x equal to 2 to x equal to 4. And this second term is the subtraction term. Now, if you look carefully at the discontinuity function, anything before x equal to a is 0. So in this case, anything before x equal to 0 is equal to 0. So there's nothing before x equal to 0, meaning that we can simply replace this term here by 1. Therefore, we arrive at 3, and then this term here is simply brought over to the second line. Now let us compute the shear force function. This is the formula that is being copied from the previous slide. Here, take a look that this is Qz, which is simply the loading function that was computed previously. So just sub in small qx into this integrand here, and we obtain this integral. The integration is from 0 to x. And this is a summation of all the applied loadings in the z direction. First, if you look at the diagram, we have the concentrated force 3 kN applied downwards. And since downwards is positive, so this term is positive, applied at x equal to 3. And then next we have the reaction force at point A pointing in the z direction. So this is x minus 0. And then we also have the other reaction force Fbz at the end of the beam at point B. So it's x minus 4. So after integration, we obtain minus 3x plus 3x minus 2. This power 0 becomes power 1. And then this term is simply brought over here. And for this term Faz, because it is x minus 0, so we can simply say that this term here is equal to 1. And then for this term here, Fbz, we can ignore this because it happens at the end of the beam. It is jump of the shear force at the end, and this term here will not appear in the moment expression. So we can simply ignore this term. Let's copy the expression for Qx over to the next page, okay, where the Faz term is actually our unknown. Now let's figure out what is our moment function using the formula given previously. The expression in these square brackets is simply the Qx function above, and there are no applied couple moments. So after integration, we arrive at this expression here, where this minus 3x squared over 2 plus this 1 becomes 2, and then you bring down 2 as well. This power 0 becomes power 1, and there's x here. Next comes the boundary condition. Which is necessary to determine our unknown f(a)z). In fact, we know that from the figure that at x equal to 4, there's no bending moment. So we write this as m and x equal to 4 is equal to 0. And then we sub in the value of x equal to 4 into this expression for the moment and set it equal to 0. From here, we are able to calculate what is our unknown reaction, f(a)z), which is equal to minus 21 over 4. Now that our unknown reaction force is found out, we substitute the value back into our expressions for the shear force and the bending moment, and we obtain the following two expressions. We are now ready to plot our shear force function and bending moment function, but first we have to figure out our loading function. Recall that the expression that relates the distributed loading to the shear force is this expression, minus qx is equal to dq over dx, where small q represents the distributed loading and big Q represents the shear force, meaning that the gradient of the shear force function is equal to negative of qx. So for convenience, we will usually reverse the sign of the loading function so that the positive q-axis points downwards. We know that the loading is positive from x equal to 0 to x equal to 2. So on the loading function, it is also positive. Positive here is, remember, below the x-axis. So you simply draw a rectangle, and this value here is our 3 kN per meter, and this is 2. We can now proceed to sketch our shear force function, where this is big Qx. At x equal to 0, from the above expression for the shear force, if you sub in x equal to 0, you find that all these first three terms are 0, leaving you 21 over 4, which is around 5.25 at this point. So at x equal to 0, the shear force is 5.25 kN, and we know that the gradient of your shear force function is equal to negative of qx. And since qx is here, we treat it as negative. That's the reason why we invert the qx axis. So if it is constant and negative, this means that the gradient of your shear force function is also constant and negative. And by how much does it go down? In other words, what's the change in value of the shear force function from x equal to 0 to x equal to 2? In this case, you can easily find out using integration. So delta q is actually equal to minus qx dx. And the area of this rectangle is actually 2 times 3, equal to minus 6. So from here, on the shear force diagram, drops down by 6 units. Something like this, where this is actually 5.25 minus 6 is around minus 0.75. So this minus 0.75. And then beyond x equal to 2, there's no loading here, meaning that it is the gradient is constant and 0. Okay, 0 and constant. This goes on all the way until x equal to 3, when you realize that there is a concentrated loading of 3 kN in the positive z direction. So on the shear force diagram, it is supposed to be a negative drop by 3 units. So this is minus 3.75. And then beyond x equal to 3, there's no more applied loading, no distributed loading, is all the way until the end of the beam at x equal to 4. So from this diagram, we can deduce that the internal shear force at the end of the beam at x equal to 4 is actually minus 3.75 kilonewtons. To find out the intersection with the x-axis at this point here, where the shear force is 0, we simply draw the triangles. This, we call this x, this will be 2 minus x, this is 0.75, this is 5.75. Using similar triangles, this is x over 5.25 equals 2 minus x, 0.75. And this will give you x equal to 1.75. So exactly at x equal to 1.75, the shear force is 0, and this fact will come in very useful when we sketch our moment function. Recall that the shear force function is equal to the gradient of the moment function. Now, the figure on top is the shear force function which we have just obtained. The diagram below represents the sketch of the bending moment function, which we are going to sketch now. From x equal to 0, we know that the moment at this point here is 0 because it is a pin support. And then looking at the value of the shear force function from 5.25 to minus 0.75, it is decreasing. It is decreasing from 5.25 until x equal to 1.75 when it goes to 0, meaning that the gradient of the moment function goes from a positive value and then it becomes more and more gentle until it reaches 0 gradient at exactly this line here, x equal to 1.75. So this is calculated previously. Let me now draw the bending moment for this portion of the beam. It looks something like this. Remember that the gradient here at this point has got to be equal to 0 because the shear force is 0. And from x equal to 1.75 to x equal to 2, it becomes more and more negative, meaning that the slope of the moment function becomes steeper and steeper, and it's also negative. So it looks something like this. Okay. And then from x equal to 2 to x equal to 3, it is constant and negative, meaning that the slope is also constant and negative. So it looks like this. And then from x equal to 3 to x equal to 4, it is constant and negative. It is more negative, meaning that the slope at this portion has got to be steeper than the slope within this portion. So it appears slightly steeper. Yep. So that's how you sketch the graph. Now for the values, how do I get 4.59 at x equal to 1.75? Okay, I simply calculated the shaded area for the shear force diagram, and the shaded area here is actually the triangle, which is half times 5.25 times 1.75, giving you 4.59. And then you can go on also to find out the value at x equal to 2 by calculating the area of this smaller triangle and see how much the moment changes, and so on for the other values here. By calculating the area under the shear force diagram, we are able to calculate the change in the bending moment, since the change in the bending moment is related to the integral of the shear force. Okay, that's it for this lesson. Hope you enjoyed the lesson, and see you.